All right. So in our last class, we talked about some discrete probability distributions, and we concluded on some common discrete probability distributions that are commonly used, and we looked at their properties, their characteristics, and then we also gave an assignment for us to be able to identify uh, which of these distributions we can assume or we can choose to use to represent a particular data set. And I believe that we have gone through that, and we have a clear understanding on situations that warrant us to use specific probability distributions for for our calculations. So before then, there was this assignment, this example that was given, and Mrs. Eben made an observation concerning the assignment, the class example, and I did said I was going to get back to her concerning that. So briefly, before we delve proper into today's class, I would like to uh, talk about that particular class exercise so that we will see why it was presented the way it was presented. So if you permit me, I would like to present my screen right now. But the screen I'll be sharing now will be for the last class before we will delve into today's class. All right, can you confirm if you can see my screen? If you can see my screen.
Yes, yes.
All right, that's great. So the challenge was on the geometric distribution. So we gave the discrete geometric distribution uh, with parameter p. The PMF, or the probability density function, is given by the quantity here. P of s equals to k. That's probability of the random variable equal to the value that the random variable can take. We say it equals 1 minus p, or q raised to the power of k minus 1 times p. So we say we can use this as a probability density function to model the behavior of the random variable in that experiment. So we gave this question. We say a telemarketer makes repeated calls to persons on a computer generated list. Uh, we say the probability of making a sale on any individual call is p equals to 0.10. Successive calls are independent. Let x be the number of unsuccessful calls before the first sale. Then x has a geometric distribution with this quantity. Now, before then, we know why this is a geometric distribution. Why this follows a geometric distribution from our last class, we have explained, and I will say we are looking for the failures before success, the number of failures before success. We say let x be the number of unsuccessful calls before the first sale. So we're trying to model the first number of failures before the first success, and that makes it a geometric uh, distribution. So here we have following the PMF of the geometric distribution, we're supposed to have q raised to the power of k minus 1 times p. But as we can see here, we have q raised to the power of k, no minus 1, times p, which is 0.10. And we know how we were able to get q, since we already have p. P is equal to 0.10. We say q is 1 minus 0.10, and that gives us 0.90. So we have 0.90 raised to the power of k, but from the formula we have k minus 1, and then we have 0.10 as p. All right. Uh, Mrs. Eben, are you with me?
Oh, I'm with you.
All right. So the reason why it's being presented this way is because actually this is we have not even, they have not we have not even asked the question here. We have not even asked, because they are supposed to be like two questions. but we're trying to see to be able to identify. We're not actually solving here, but we're trying to identify that it follows. It assumes the geometric distribution. Now, following from the geometric formula, we see that it's supposed to be this value for k equals to 1, 2, 3 continually, and then you see with that you now put 0 otherwise, right? So that's if it is 0, then it is the other way around. And that is why you see here, if say for instance k is 0, it will be 0 minus 1, which should be minus 1 raised to the power of minus 1, which will not give us what we are looking for. It will not work in this situation. So k must always start from 1 continually. If k
That's what
starts
I
from
was saying. That
yes,
in this instance,
mm,
K will always start from 1,
yes,
not
because
0.
if not 0, because if k starts from 0, we are going to
Then
have a
it will
negative value.
be to the power of minus 1. So I was
So which
just
will not work.
following the formula, believing that
Yeah.
if K is equal to what's it called 0, then
Mm,
it will be. So that's why they put otherwise. So that's just
all
what
right.
I want to confirm.
Yeah,
Yeah.
nice. All right. So in this case, the reason why we not put k minus 1 here is because we say that k ranging from 0, 1, 2, 3. But we've already defined from the formula that if it is 0, then it is otherwise, which means it will not work. So k must always start from 1, and that is why we do not put k minus 1 here, because we use 0 here. If there's no 0 here, we have to put the k minus 1 here. And that's the reason why we're having q raised to the power of k. You understand now, right? But for the purpose of solution, we're not considering because it's we're not considering because here it's not possible that he's going to, if he makes repeated calls, it's not possible that he will get first sale with 0 calls, right? I don't know whether you are following. If there's no call, 0 call means there's no call. If there's no call, there's no it's not possible for him to make any sale. If there's if
Yes,
it
yes,
uh,
accepted.
if
Yeah.
there's 0 call, then it's not possible for him to make any sale. So the calls must start from 1 call. Maybe he makes sale at the first call, or the second call, or the third call. So that's why they represented it like this in the textbook. But for the sake of solution, take for instance, uh, there are questions, because this same question can come with some other question. I find the probability that he made dash sales at the fifth call. That's when we now start finding the probability of uh, x equal to 5, or x greater than 5, or x less than 5, or x greater
Yeah.
than or equal to 5, and so on and so forth. Yeah, so that's why they represent it this way. But for the sake of calculation, you have to use the k minus 1, and you will not start from 0. Yeah. So, but it is clear that this uh, experiment follows a geometric distribution. All right. So with this, if you permit me, so that we'll start today's class now.
All right.
Yeah. Or is it possible that we take turns to share? Because we say in our last class that we are going to, in this class, we are going to see how why you give reasons why you said that the particular situation follows the set distribution. So let's quickly go to the assignment and then take some few minutes and talk about it, if you
Okay.
permit me. All right. So, or should I allow you present your
It's a
solution?
general class. Everyone should kind of, I mean, that's the way I see it. I don't have any what's it called? um I didn't develop anything for it. I only jot down my reasonings to say, okay, for this one, which even you've treated the first five, if I'm right.
Yes,
So
yes.
yeah, you've treated the first five. So it's
Yeah,
just
exactly.
the other one. So like you said, the first four that you've treated. So maybe in case you ask, and if we have any answer to it, you listen. If we are correct, we go ahead. That's why
Okay.
class is good. And
Yeah,
anybody
exactly.
that have a contrary reason, then my
Yeah,
suggestion.
can share it and give us his reasons.
Yes, that's the
All
way.
right. If that's the case, let's go straight at it, and then I believe everyone have studied it. Mr. Osawo, you have gone through it, sir. Have you gone through it, sir?
I've not. Oh,
Ah,
I've not. But you can continue. You can continue. I've not.
okay. If you had gone through it, it would have been better for us because you will understand what we're
I've
talking
not.
about. You can contribute. So please, let's try and be following the class. Let us not pile it up because when we pile the material at the end of the day, we may be
Yeah,
rushing
you're
because
very correct. You're
yeah,
very correct.
the goal will be defeated because we really want to understand, not just to just study
Yes.
some set of written down things and just write them in exams or tests. All right.
Okay.
So it's okay.
Thank
So
you.
please let's try. Let me ask. How about Mr. Kainde? I mean Mrs. Kainde.
So, okay, I think I'll pass because I've actually been somehow held back in the office for quite some days now.
Okay. So you are
So
saying
my
you have not gone
apologies,
through it.
please. I'm really very
Okay.
sorry.
Okay. All right. So, class, is
Well,
the apology accepted?
Yes, so it's accepted.
All right. All right. All right. Okay. Since all right, it's okay. It's okay. All right. So, if that's the case, let's watch ahead. So, let's look at this one. We say an auto insurance company has determined that the average number of claims against the comprehensive coverage of a policy is 0.6 per year. What is the probability that a policyholder will file A, one claim in a year, B, more than one claim in a year? So, who can tell us which probability we can assume and give us reasons?
I can give it a try.
All right, go ahead, sir.
I hope I'm not wrong. It's just a try. Um, I will take this to be poison.
So he was just trying to embrace the fact that when
Hello?
the new wife
Yeah, we can get
Okay.
you. Go ahead, sir.
Okay. Yeah. So I will take this to be poison uh, distribution.
Okay, is it because it's written up or you have your reasons? So, what are your reasons?
Okay. No, 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 no. It has. Oh, I didn't even look at that. Honestly.
All right, all right. So, what
Honestly,
are
I
your
didn't.
reasons, sir?
Yeah, because um, when I have the average, is because of that average claims that have been given, uh,
Okay.
particular within a particular slot
Yeah,
of times.
specifically
So that
because it is
I
it is
think that
rate
it
since they
be
put
poor.
per year because it is a
Yes,
rate.
yes.
All right, all right. Okay, that's all.
I
All right.
think
Yeah,
that
fine,
is all.
fine. That's correct. That's correct. So most times, immediately you observe a rate in a particular question, you know that we're talking about the Poisson distribution. Yeah, all right. That's correct. What about the 518? We say policyholders of an insurance company file claims at an average rate. Okay, this one too is straightforward. So let's look at another one. All right, 523. If you roll a pair of that fair dice, the probability of getting an 11 is 1 over 118. If you roll the dice repeatedly, what is the probability that the first 11 occurs on the eighth roll?
Okay. Yeah. Should I also give that a try?
Yes, go ahead, sir.
Okay. So for the first 11, so first of all, here, um, getting an 11 is the event. So that is like the success.
Yes.
Uh, Probability is 1 all over 18. So
Okay.
if I want to get that success on the eighth row, what that means is I must have first of all done 7 successive rows that did not result in the 11.
Success. Yes.
And it is the last one that resulted in the 11.
11.
And if probability of success is 1 all over 18,
Mm.
then that means probability of failure will be 1 minus 1 all over 18, which is 17 over 18.
Okay.
So the probability here will be 17 over 18, everything all to power 7 times 1 all over 18. I hope
Okay, so
I
yeah,
didn't.
yeah. You're on point. You're on point. That's geometric. It's geometric because to get 11, you must the first die, because you are rolling a pair of fair dice. One must be 5 and the other must be 6. That's the
Oh,
situation.
sorry. I didn't look at that. That's sorry.
Yeah.
Can I take that again then? I think
Yeah.
I
No.
missed that point.
Yeah, but you are on point, Sha. You are on point, Sha. But
Okay.
yeah, you missed
Okay.
a bit, but you are still on point.
Okay.
Sorry, can you repeat that? Because I thought I was in line with Mr. Coinda's view. So you said what?
Okay. If you roll a pair of fair dice, a pair making 2 dice,
Yeah.
and we're interested in probability of success, which is 1 over 18, but that success is getting an 11. And to
Okay.
get an 11, the first die must show 5 and the second die must show 6.
6. Yeah.
So that will give us an 11.
Yeah. But
Now, but
but does it really affect our calculation? No.
yeah, it does not affect our calculation. That's why I said he was correct, but
Yeah.
yeah, that's why I was saying he was still right now.
Okay.
Right?
Okay. So the next one, I had a problem. Not that I have a problem, but I just want to confirm. So
Okay, all right, go ahead.
no, that's what I'm saying. It's the
Let me
same.
read it.
Okay.
An experiment consists of drawing a card at random from a standard deck and replacing it. If this experiment is done repeatedly, what is the probability that the first hat appears on the 5th draw?
So
B, the first ace appears on the 10th draw. Now, this is a geometric distribution. Why?
yes,
Because if you keep on drawing card and returning it, we have 52 playing cards.
always yes. So the
So once
probability will be 1/52. Is that?
a hand. So if you keep on doing, we're getting 1 over 52, 1 over 52.
That's what I wanted to confirm. Yeah.
Yeah. But they now say, okay, we're looking for the probability that the first hat appears on the 5th draw, which means you must have drawn the first draw, no hat, second draw, no hat, third draw, no hat, fourth draw, no hat, and then the 5th draw, you get a hat. So that makes it geometric, because geometric is talking about number of failures before the first success.
And so our S will be equal to, or let me say, the first success appear on the 5th means that we've gotten like 4 failures before. Is that?
Yes, yes.
Okay, so the probability of S equal to 4 will be 1 minus P over 3, which is the 1 minus P will be 51/52.
Yes.
Aha. Okay then.
All right. So
I have a comment on this 5.24.
okay,
I
go
think
ahead.
there is an assumption here that
Okay.
everybody understand the number of cards in a pack of
Playing cards.
in a deck, as
Yes.
well as composition. So I'm thinking, because it's not everybody that will know that there is a heart, there is a
Okay, yeah, there's spade,
there is
there's
a spade, and so on and so
diamond,
forth.
and so on. Yeah, exactly.
Maybe the composition could always be disclosed or be given, so that it helps in
Okay, yeah, in easy.
attempting the
Yeah, you're
question.
right. There are the out of the 52, they are shared into I think it's 12, 12 or something like that.
Yeah.
Yeah, 12, 12 or well, something like that, yeah. All the cards. Because we have 4 of them. We have the diamond, spade, heart, and then the other one. So if you divide 52 by 4, you get the number in each of the what will I say? Each of the different cards, different shape.
Is
Cards.
there is there no queen or king? I don't know. I hope I'm
No,
not mixing it
even
with chess.
you are still correct.
That's
There's king,
yes.
there's queen, there's joker, there's so on and so forth. But each of these king and joker, there's king of hearts. So
Okay.
if we're talking about hearts, there's king of hearts, there's king of spades, there's
Yes.
king of and so on. So if we're talking about hearts, it encompasses whether it is king or joker or normal number or so. I don't know. Do you get what I'm talking about?
Yeah. I
So
thought because I look at the fact that it's replacing. So that's why I felt that whatever it is, because if it's not replacing, that's where we have to be
We're subtracting.
considering the component of the what's it called, standard deck, because then we have to be taking away the number of art and then consider what is remaining. But
Yeah,
since it
exactly.
says replacing, so I felt that okay, whatever
It's,
we pick, we
it
can
will
put
always
it.
be
Yeah,
13. It will
yeah,
always be 13 over 52
yeah,
to take a maybe a particular hat or spade. The
yeah,
probability is always 13 over 52, which is 1 over 4. 1 over 4 in each case.
yeah. But
Yeah.
now that it's replacing, it's going to be 1 over 52. That's why I was trying to find out. Is that?
Okay, yeah, yeah. No, it will still be 1 over 4 because if we're talking about we're looking for hat,
Yeah.
and you don't have 52 hats, you only have 13 hats in the card in the deck.
Yeah. I think that's where Mr. Conde is going on. Let me say, because if we have the whole pack, which is 52,
Mm,
and they said randomly picking one and replacing it.
yes.
So, the card is there, you just pick one. That's why I
Mm.
said I don't think the first art appears. So, are we going to consider the number of hearts in this case? Because I was thinking it's just a random
No,
pick.
no. It's not. It's a random pick, but we're actually our success is hard now. You know,
Okay.
here now we will get a probability of success, just like we have 1 over 18 years probability of success for getting an 11, right? So the probability of success here will be 1 all over 4, which is 13 all over 52, because we are interested in heart. Do you
Okay,
understand now?
that's where I asterisk it. That was like, okay.
Yeah. So here we're interested.
Okay.
Our success is heart, which is 1 all over 4 or 0.25. So
Mm.
just like here, you see here they give us 1 all over 18 as probability of in this question that's 523, but 524 now our probability of success is 0.25 or 1 all over 4 or 13 all over 52. So if you replace it in the formula, you can get what you're looking for.
Mhm.
Yeah, and it will
Oh,
be easy. It will always be easy. It won't change. The probability of success will not change because we are replacing the card.
okay. That I'm so confused there. So
And
I
so
think that
if we
was
were
where I
not
mixed it up.
okay, if we were not replacing the card, we'll be subtracting.
Yeah, I
We'll be
know.
subtracting.
So I was thinking, I was looking at the whole pack as a
Okay.
whole, that we're just kind of, if we pick one, yeah, there's art there. Maybe I don't know if you understand what I'm trying to say. If you
Yeah, I
pick
understand.
one,
Hmm.
we are now left with 51.
Hmm. Yes. So,
So,
but if from that first one, if it is not hard, then it means the what is remaining now is 13 over 51 because there's still hard inside. That's
okay.
if we're not replacing. Do you get?
Yeah, yeah.
Then if we pick another one, that's the second one, and we do not get heart, then that will be 13 all over 50 because there's still 13 hearts inside.
Okay.
So
But
we
since
keep
we are
on going that way.
replacing,
But since we are
okay.
replacing, then it will always be 13 over what do I say? 13 over 52 plus the next one again. The second one will be what? Also 13 over 52 plus the next one. Do you get before we now get, and then we'll now do 1 minus. But if you put it in the formula for geometry, it will be easier.
Okay.
Is that
Okay.
clear now?
Okay. Okay.
All right. So I think if we can also do that for the rest. So,
Okay, so that means the second one now is not the probability for the second one is not. I mean, oh, that's what this that probability I was so confused about.
okay. All right. So can we continue?
Yeah.
Okay.
Yeah. I think that's yeah.
All right. So let me switch to my next device. I think there's no light
No,
and
there's
the
this
stars.
one that if it sells, I think I needed to just confirm something there, just to be
Okay.
sure. Yeah.
Okay. All right. They say if each sale made by
Yeah,
the
I think
person in
yeah. Exercise 17. I mean exercise 30.
5:30. Okay. They say a
Uh-huh.
telemarketer makes successful calls with probability 0.20. That's probability of success.
Yeah.
What is the probability that her fifth sale will be on her 16th call? Okay, I've not actually checked this one, but
Will be,
what's can you share your ideas?
but you've taken the question away now.
Yeah, yeah, let me share it again. My other device has gone down.
Okay.
Is it clear now?
Yeah.
Okay, let me go there. All right. Okay. All right. This is actually negative binomial.
Yeah.
Hmm.
So I just wanted to find out what, just to be sure if I'm right with what I call my R, which is
Okay.
the, yeah, that's just to be clear. Even if we start
Okay.
from the 530, the telemarketer, because the 530 went to the next one, just to share the idea of what R is at that rate.
Okay. Can you remind us what do we say was R?
That's okay. With what I put down, I said my R will be equal to 5, while my K is 16. As in, if the probability of S equal to K, you understand what I'm saying? So I
Yes,
just said
yes.
the K, the number variable that we're looking for is 16, and then the R there would be 5, though we're giving the probability, so we don't have problem. It's just I was missing it up. I was like, am I right with the suggestion that is it
Okay.
the K that is 16 or the R that is the fifth? So
Okay. All right. If you follow through the formula, you will know which one is which.
no, that's
But
where I know there's a formula that goes with it. That's where I
mm,
wanted to find out which one, if I'm really right. I know negative binomial goes with the uh probability of S equal to K, K plus R minus 1 combination K, P raised to power R. So
mm,
in the, and then 1 minus P raised to power K. So when I was reading through, I wanted to be sure that what is that our fifth cell will be on our 16th call. So I was like, I hope I represented it well. That the K is 16 and the R is 5. That's just what I want to find out.
okay. All right.
Just the
Uh,
if I got the interpretation very well. Ha. Someone
Okay.
wants to come in. Yeah.
Okay. Go ahead. Go ahead, sir.
Okay, thank you. I just want to add to what Ebu said.
Okay.
Um, I'm at times I'm not too good with formulas, but I like to always take things from the first principle.
Yeah.
Okay.
Looking at this question, and sorry, just the way I'm thinking of it in my head,
Okay.
I'll split it into two.
All right.
The 16th call, fifth sale on the 16th call, it means there must have been four sales in the initial 15 calls.
Yes.
That four sales can come in any number of ways. So I will take that 15 calls as the normal binomial, and I will do my normal 15 combination 4 times raised to power 15 minus 4 and success raised to power 4. Then I will now multiply it by the one call that is successful on the 16th call to get the formula. So that is the way I'm looking at it. 14 combination 4 times q raised to power, sorry, 15 combination 4 times q raised to power 11, then times p raised to power 4, then times p.
Okay. Uh. eh, Okay. Let's see. I've not actually checked the question properly, but I'll check. Then we'll come and talk about it in the next class if there's time.
Okay. So
Yeah.
it's just the last two there. Thank you, Mr. Quindi. It's just
Thank you, sir, for your
the
contribution.
530 and 531. I just want to be clear about.
All right.
Okay.
So I think we will stop here and start the class for today. So I don't know if my screen is visible now. Are we there? Is my screen visible? Hello.
Not yet, please.
Okay. Well, how about now?
I don't know. On my side, I can't see it properly.
Okay. Let me go through the process again. Just give me some minutes.
Okay.
I'm sharing now. How about now?
Yes.
It's clear, right?
Yes.
Okay. Thank you very much. So thank you all for your contributions in the last class, and then for I'd like to appreciate also those who have done the assignment. You have really done well. And then I will like to encourage those who have not yet done the assignments to please go ahead and do them. It will go a long way in helping us understand what we are doing in this class. So today's class on probability theory and distribution, this is lecture 5. I remember my humble self, Anzaku Jacob Patrick, and we'll be taking the course with Ilyasu 80. So the our table of contents for today is as follows. We have the recap, we have today's discussion, we have introduction, we have standard univariate continuous distributions and their properties. We have properties of some univariate continuous probability distributions. We have the applications, we have summary, and then we have the conclusion, and then we have exercises for the next class. Uh, in this class, especially in this probability theory and distributions, we try as much as possible to understand how probability theory works. You remember when I was explaining earlier on that for any experiment or for any event, whether it is in actuarial science or in insurance, we look at them statistically or mathematically as events or experiments. And in each experiment or in each event, that is where we can generate data. And that data that we generate, we call them the random variable because they vary. And then they can take any value or any form. And because of that, we say we also need to understand the behavior of these random variables. And we say what will help us model the behavior of this random variable is probability distribution. So probability distribution is actually the tool that we use to help us model and to understand the behavior of this data generating process called events or experiment. So we talked about that of the discrete probability distributions. We say discrete probability distributions are probability distribution of counts. They help us measure count data, a data that has a specified integer. And we say in practical sense, we look at, or in mathematical sense, we look at or in theory, we look at the discrete probability distributions as integers, while we say we look at the continuous probability distributions as decimals. That's in simple or layman understanding. Now, in the last class, we talked about the binomial distribution, which talks about success or failure. And we say it arises from the Bernoulli distribution. And we say for the binomial distribution, when you repeat an experiment n times, when you have success or failure, then it leads you to a binomial distribution. Whereas for the Bernoulli distribution, we say when you repeat the experiment only once, it gives you the Bernoulli distribution. We also talk about the discrete uniform distribution. So there's also the continuous uniform distribution. We talk about the discrete uniform distribution. We talked about the negative binomial distribution. We also talk about the Poisson distribution. We see a distribution of waiting time, and when we have rate, average rate, oftentimes you should tell you that you are using the Poisson distribution. And then I will also talk about the geometric distribution. I will say that the geometric distribution models the number of failures before the first success. So we also gave examples, and we understood their properties, their CDF, their PDF, their mean, their variance, the special case of some of the distributions, and so on and so forth. So today we will be talking about some continuous probability distribution, some continuous probability distributions. Remember, we see that we have two specific probability distributions, which is the discrete and the continuous. So we have dealt with the discrete probability distributions. So we want to delve into the continuous probability distributions, even though in our what do we call this class? The seminar in actuarial mathematics. We have talked about some of these distributions, and we have even started working on real data. But here we will see how we can understand most of the distributions, especially the common ones, and also see how we can uh, understand their behaviors. Then, when we come for the seminar in actuarial maths, we will be able to use real lifetime data in insurance and do some calculations with them using the Python and other programming languages if possible. So today, in continuation of the continuous probability distribution, we're continuing here. I believe we are all together. Are we all together? Hello, are we together?
Oh, yes, yes.
All right, fine. So that it will not be as if it seems as though I'm the only one talking or I'm the only one here. So that's why I want to uh, get our feedback.
Okay.
Okay, all right, thank you. So let's continue. Now, a brief introduction on continuous probability distributions. Remember, we say that we just introduced a bit when we started the class, but let's just give more of the introduction now. Continuous probability distributions play a fundamental role in statistical theory and applications. And unlike the discrete probability distributions, which deal with random variables taking on distinct values, just like I explained, continuous probability distributions handle variables that can assume any value within a given range. So we see that's the difference, the major difference between discrete probability distribution and the continuous. The discrete gives distinct values. It measures, it deals with random variables taking on distinct values, integers, while the continuous deal with random variables assuming a range or a value within a range. So that makes it continuous. Maybe 5 point something or some point something. So it makes it continuous. It is not distinct or discrete. In this class, we explore the key concepts and properties of continuous probability distributions, focusing on essential functions such as, so our focus will be more on the probability density function, the cumulative density function, the mean, and the variance. There are some other properties, just like I explained, because we know that probability distribution and theory is very, very wide. In fact, is a large area in statistics, especially. There are people who major or who are professors of probability distributions theory and so on and so forth. So it has very large application. So if we say we want to go through all the properties, we may not completely finish them. So, but we need to go through the ones that are very important, especially the PDF, the CDF, the mean, the variance, and then maybe as we go further, the moment generating functions. Now, so these functions provide insights into the likelihood of a random variable falling within specific intervals. One of the central elements in continuous probability distribution is the PDF, which we denote as small f of x. So when you see small f of x, it is the PDF of continuous distribution. And when you see capital F of x, we're talking about the CDF, or the cumulative distribution function uh, of the distribution. And the CDF complements the PDF by providing the probability that a random variable is less than or equal to a specific value. Now, to illustrate these concepts, we will delve into well-known continuous distributions such as the normal distribution, the exponential distribution, the uniform distribution, and others. Now, each of these distributions has its unique characteristics and applications, which make them valuable tools in statistical modeling and hypothesis testing, or which makes them valuable tools in actuarial science and insurance. Now, let us begin our journey into the fascinating world of continuous probability distributions. All right, mathematical notations, I've explained this. We use small f of x like this, or f subscript x of x like this to represent the PDF of a continuous distribution. We use capital F of x as in here, or p of open bracket x less than or equal to x. It is continuous, so it cannot be specifically equal to. It is only discrete that has strictly equal to, but for continuous, it has less than or equal to. So it is continuous. Makes it in a range. So that is, so we have something like this. Remember, for the discrete, we only put the random variable x is equal to the value that it can take, small letter x equal to. But for the continuous, we have less than or equal to, and that less than makes it a continuous probability distribution. Also, the mean for the continuous probability distribution is represented by mu here, or we have expectation of x, and which mean though looks similar with that of the discrete. But when we see things like this, we understand that what it is talking about. All right, the variance is given by sigma squared, or variance of the random variable x, and then the standard deviation is given by sigma, or the square root of the variance of the random variable x. All right, so an introduction to univariate continuous distributions. Now, remember in one of our classes, we talk about three, I don't know whether it's here or in the other class, but we talk about three random variables. We talk about the univariate, the bivariate, and the multivariate. I remember something like this. Univariate means it has only one variable. Bivariate, it deals with two variables. Then multivariate, it deals with three or more random variables. So that's just the difference. So a univariate continuous distribution involves a single random variable. The key characteristic of a continuous distribution is that the random variable can take on any value within a range or interval. Let us not forget this, because this is just the difference between the discrete and the continuous. The discrete takes value within a certain range or interval, rather than being restricted to distinct or separate values. Now, continuous distributions are often described using probability density functions, and the probability density functions specify the likelihood of the random variable taking on specific values. The likelihood of the random variable taking on specific values. Then also the area under the PDF curve of over a certain interval represents the probability of the variable falling within that interval. So that's the use of the curves. Anytime we do any probability plot of any of the distribution, we're trying to say, okay, the random variable has a probability of falling within the range of that interval or that curve. All right, so here are some examples of the standard univariate continuous distributions. Remember, we say why it is univariate is because it deals with a single random variable. Now, as we delve more and more into the course, we will look at other bivariate continuous distributions and discrete distributions. So, In the continuous univariate distributions, we have the uniform distribution, we have the normal distribution, we have the student t distribution, we have the chi-square distribution, we have the f distribution, we have the exponential distribution, and we have the gamma distribution. We have come across the student t distribution if you are looking at some uh, tests like the t-test. We have come across the chi-square distribution, and then we have come across the f distribution in one or two instances. So let's talk about the uniform distribution. Remember, there's the discrete uniform distribution, which was talked about. This is the continuous uniform distribution. The continuous uniform distribution is the simplest of the continuous distributions. It is characterized by the following properties. Uh, it is denoted as U of AB, U into bracket AB, uh, and it is defined over the interval A, comma B. This is a closed interval A, comma B. This is a closed interval A, comma B. If we see a square bracket, it's talking about a closed interval where A and B are the minimum and maximum values of the interval. So A is the minimum value, B is the maximum value, since A comes before B, respectively. The probability density function PDF of the uniform distribution is given, continuous uniform distribution is given by the PDF f of x, small f of x is given by 1 all over b minus a. That's if the value that the random variable takes lies between a and b. But if it is outside a and b, then it is zero otherwise. So once we are trying to deal with the continuous uniform distribution and the random variable that we are looking for is zero, or it lies outside this interval of a and b, then the probability density function is zero. Now, some properties of the continuous uniform distribution. It has a constant probability density function. That is, uh, the PDF is constant within the interval, closed interval a comma b, and it equals 1 over b minus a. That's for the uniform distribution. In fact, the uniform distribution is the simplest continuous probability distribution. Now, two, equal probability. All values within the interval a comma b have the same probability density, resulting in an equal probability of occurrence. We will look at examples. Uniformity. The distribution is uniform. That's why it is even called uniform distribution, meaning that this is why we say uniform. This is what it means to be uniform. It means that the probability of observing any sub-interval within the range is proportional to the length of that sub-interval. Right? Maybe that might need extra explanation, but when we see examples, we understand more. Then the CDF of the cumulative distribution, it is zero if x is less than a. It is x minus a over b minus a if x lies between a and b. Then it is 1 if x is greater than b. It is 1 if x is greater than b. So if we are considering any event that does not lie in the interval but is greater than the larger range, the maximum, then we know that the CDF is 1. Then it is the cumulative distribution function is 1. It means that we have sum from the interval a to b and more. So that gives us 1. Mean and variance. The mean mu and variance sigma square of the continuous uniform distribution are given by mu equals a plus b over 2, and then the variance is given by sigma square equals to b minus a all squared over 12. Now, there are mathematical and statistical processes that generate all this mean and variance. But just like we say, for the sake of this class, we want to understand so that we more of the practice and how we can apply them rather than understanding the uh, little or intricate integrity mathematical expressions that derive some of these uh, properties. Now, one important thing that we should note here is that uh, we should try and understand the, the mathematical representation of these distributions. We might not necessarily cram them, but let's try and understand so that when we see them, anywhere we see them, we can identify, oh, this is for the continuous, this is for the beta, this is for the gamma, and so on and so forth. All right, the normal distribution. The PDF of the normal distribution is given by this. Here we see that the PDF of the normal distribution has two parameters, mu and sigma. Mu is equal to is the mean, while sigma here is the standard deviation. And one key thing about the uniform distribution, the normal distribution we should know is that it is normally distributed with it transforms to the standard normal distribution when mu is equal to 0 and variance is equal to 1. So, but we should know that anywhere we see an expression like this, it is talking about the probability density function of the normal distribution. Now, the CDF of the normal distribution is given by this quantity here, 1 over 2 into bracket 1 plus ERF of what we have here. Then the mean is mu, and then the variance is sigma squared. Now, the exponential distribution has PDF given by this. Now, there's a reason why I'm not putting, not put enough information here. But remember, we have actually talked about the normal distribution with in seminar for actuarial mathematics. If we have been in the class, we see that we have talked about some of the distributions. So the ones that we have talked about there, we will just bring out some of the properties and list them and just try to refresh our memory. We may not actually give enough information about them. So, but for the normal distribution, let us just put it at the back of our mind that if we see a quantity like this, it's representing the PDF of the normal distribution. This is representing the CDF, and then the mean is mu, while the variance is sigma squared. Now, for the exponential distribution, we have it arises from the exponential function, which is e to the power of lambda x, which is the exponential function, and then it has one parameter. It is parameterized by lambda, that's the exponential distribution, and it gives us lambda. Remember, lambda is the rate. So some of these distributions, they have similarities. Remember when we are talking about the Poisson too talks about rate, and it almost looks similar to this one, but not the same. They may have similarities, but they are not the same. But the one peculiar thing about them is the rate. The Poisson is discrete, while the exponential is continuous. Now, the PDF of the exponential distribution is given by this function, lambda multiplied by e to the power of negative lambda times the value that the random variable can take, which is x. That is, if x is greater than or equal to 0, and it is 0 otherwise. That's if x is less than 0, then it is 0. The CDF is given by the function here, 1 minus e to the power of negative lambda times x. If x is greater or equal to 0, and it is 0 otherwise. The mean of the exponential distribution is 1 over lambda, and the variance is 1 over lambda square. I'm sure we have talked about this exponential distribution in the last class of in seminar for actuarial mathematics. Okay, the properties of the student's T distribution. Now, the PDF of the student's T distribution is given by this function here. The function looks ugly, but our duty is not to cram, but to understand that if we see something like this, we're talking about the student's T distribution, where V is the degrees of freedom. So we have with V degrees of freedom, and then it is parameterized by gamma. The gamma, this function here, gamma of what is in bracket, that's gamma of V plus 1 over 2 denotes the gamma function. Then the student's T distribution has symmetry. That's is symmetric around its mean, which is typically takes the value 0. Now, the properties of the student's T distribution continue. The mean and variance of the T distribution, the mean is 0 for V greater than 1, and the variance is V over V minus 2 for V greater than 2. We say V is degrees of freedom. So you can easily determine the mean and the variance if you know the degrees of freedom. And then we say the fourth property is that the degrees of freedom parameter determines the shape of the t distribution. So, I would have plot. I wish that I plot the plots for the t distribution. We will have seen more as v increases. We'll see how the shape uh, works. And but as v increases, the distribution approaches the standard normal uh, distribution. Now, the student t distribution has heavy tails, so uh, the tails are heavier than that of the normal distributions, especially if the values of the degrees of freedom are very small. Then it converges to normal distribution as the t as v increases, just like we explained from the shape here. We see that as v increases, the distribution approaches the standard normal distribution. And we say that the standard normal distribution has mean equal to 0 and variance equals 1. Then the critical values of the t distribution is commonly used for constructing confidence intervals and conducting hypothesis tests with critical values determined by the degrees of freedom. Now, down to the chi-square distribution. So far so good. We have talked about the continuous uniform distribution, the uh, exponential distribution, that's the continuous exponential distribution. We also talk about the normal distribution, and we talk about the student t distribution. Uh, is there any question before we continue, or addition, or contribution, more observation before we continue?
Okay, I have one.
All right, sir.
Although you actually touched it just as I was about to raise the question, the
Okay.
exponential, because I was going to say that distribution function looks familiar,
Okay,
but
yeah,
now
yeah. Let me go
put
back
it
to it.
with Poisson.
Yes,
Yeah. So that for Poisson, when it is discrete, and that when it is continuous, it's
exponential.
the exponential. So I think my understanding from your explanation is that the functions are basically the same. However, one is used when it is discrete, and the when it is continuous, we apply
Continuous.
it at the other end. I
Yeah,
hope I'm correct with that assumption.
yeah, yeah. You are correct. You are not complete, not entirely, but just have the idea. The idea is correct, but they cannot be exactly the same thing.
Okay.
They are special cases. There are different processes that generate these distributions.
Okay.
We assume different experiments or events, just like I've been explaining. My major idea is for us to understand the whole concept.
Okay.
Yeah. So,
Okay.
but they are somehow similar, because if you check, the Poisson has the exponential function, and it also has the average rate.
Yeah. Yeah.
Yeah. So, but this is continuous, and that other one is discrete. You see, the Poisson has factorial, right? I think it has factorial over
Yes.
something ahead. Yeah. So, but because this is continuous, the factorial will not actually come into play here. You can't take the factorial of decimal numbers now, or
Yeah.
or
Yeah.
what do I, or interval of numbers. All right, that's nice one, sir. Any other? Okay. If there's none, we can continue. So the chi-square distribution now. Uh, Properties of chi-square distribution. The PDF is given by this function here. Most of the functions, they look very, very ugly. If you agree with me, they are not something that you can start cramming, but they are something that you can understand what it looks like and what it stands for, and so on and so forth. So it has k for the chi-square. K is the degrees of freedom uh, parameter, is the parameter for degrees of freedom, and then the gamma function here denotes the gamma function. The mean and variance of the chi-square distribution is k, and the variance is 2k. That's the degrees of freedom is the mean of the chi-square distribution, and then 2 multiplied by the degrees of freedom is the variance of the chi-square distribution. The degrees of freedom parameter determines the shape of the chi-square distribution. So always the degrees of freedom determines the shape of the distribution. Then as k increases, the distribution becomes more concentrated around its mean. Remember that of the student distribution, we see as the degrees of freedom V increases, it tends to the standard normal distribution, and then the mean approaches 0. Then, but for here we see that, but for the chi-square, as k increases, the distribution becomes more and more concentrated around its mean. The fourth property of the chi-square distribution it is that the values are non-negative. So if you are working with chi-square distribution, you can't have negative values. Then also, the chi-square distribution is skewed to the right. We understand what it means to be skewed to the right, right? For small values. So if we have a small degrees of freedom, it will be the shape of the distribution or the plot will be skewed to the right. Will have a shape that is concentrated towards the right. That's why we say skewed to the right. That's when the degrees of freedom is small. Then the sum of squares. The chi-square distribution is commonly used to represent the sum of squares of independent standard normal variables. So we see the relationship with standard normal variables. Application. It is widely used in hypothesis testing, confidence interval construction, and goodness of fit tests. So like the T distribution, the chi-square distribution, uh, they don't they don't actually follow some processes, but they actually help us uh, to in hypothesis testing, which we are going to, I think is part of the course. We are going to look at hypothesis testing and confidence interval construction. So when you're looking at we are doing some calculations, you see they will give you some values of the chi-square and some values of the T distribution, also the values of the F distribution, and you will make conclusions and comparisons, uh, statistical inference with those values. Now the F distribution, it also has, it is parameterized by these two parameters D1 and D2, and it looks this ugly as well. We have the gamma function, as we can see. We have D1, which is the first degree of freedom, and D2, which is the second degree of freedom. So it has 2 degrees of freedom, which are the two parameters D1 and D2, and it has a gamma function. So it's easy for us to differentiate. We see that for the F distribution, it has 2 parameters, D1 and D2, and they are the degrees of freedom. For the chi-square distribution, it has a parameter which is k, and it represents the degree of freedom. While for the T distribution, it has a parameter v, which represents the degree of freedom. Both the even though here we can see pi as a parameter, but pi here we use the standard value 3.142 to represent it. So it's actually not a parameter, but that value. So we observe that the T distribution has a gamma function represented by gamma of v plus 1 over 2. Also, the chi-square distribution also has a gamma function represented by gamma of k over 2. And then the F distribution also have a gamma function represented by gamma of d1 plus d2 over 2 and these other gamma functions.
Excuse me.
Yes, sir.
Sorry, my apology. Is this gamma function
Yes.
is appearing almost everywhere? What is this gamma? What is this gamma function?
Okay.
Because I want to believe that there should also be a representation of that function.
Okay. Yeah, that's true. That's true. For now, I've not actually checked to give you a simple explanation of what the gamma function means, but I know that there's a gamma function.
Okay.
Yeah, but
So,
just I'll check. Then in the next class, I will
okay.
explain what it means simply and what it
Okay.
represents.
Okay. Thank you. At least for now, we'll just take it that those gamma, the way they are, we take them like that. Then
Yeah,
we'll get the.
exactly.
Okay. Thank you.
Exactly. You know, if you are maybe I don't know whether what your course of study, but if you are mathematically inclined, you know that there's something called the gamma function. But Sometimes we mathematicians or statisticians, we just take them without actually looking at what they actually mean. So, but I'll do that and then I will explain in the next class. Thank you for that observation. So, the mean and variance of the F distribution is given by this D2 over D2 minus 2 when D2 is greater than 2. That's when the degree of freedom, the second degree of freedom is greater than 2. And the variance is given by this quantity here, this guy here, when the degrees of freedom is greater than 4. Now, the degrees of freedom of the D1 and the D2, that's we're talking about the other properties of the F distribution. The degrees of freedom of the two of the D1 and D2 determine the shape of the F distribution. So the larger values of the D1 and D2 lead to a more concentrated distribution around the mean. Then also, it also has non-negative values. So we cannot have negative values for the F distribution. Then it is also skewed to the right, especially when you have very small values of the degrees of freedom. Then it is commonly used in ANOVA. We have heard of ANOVA, analysis of variance, and the regression analysis. Analysis of variance, if we want to check whether there is some degree of variability between some events, we can use the ANOVA, analysis of variance, and check whether there are some degrees of variability. And also whether the regression analysis, if we want to measure the association of a particular variable with its other, what do they call it now? We have independent variable and the dependent variables, one dependent variable and one or more independent variables. Remember the regression analysis, then we can also use the F distribution. So we compare it with the level of significance and then the value of the F value. The tabulated, sorry, we compare with the tabulated and the calculated, and then we can make judgment whether or not we want to accept the hypothesis or not. If we can remember, if we have done something like that before, okay, this is what it means. All right. Okay. All right. So in summary, let's look at some of the properties again. Just in summary, we have talked about the properties, but let's look at them before we now start looking at some applications. Now, remember we said that the exponential distribution has the PDF given by this lambda is the power of lambda multiplied by e to the power of lambda minus x, where e is the exponential function, or where e to the power of minus lambda x is the exponential function, and we say that x is greater than 0. This is the range, s greater than or equal to 0. So where lambda is the rate parameter, remember lambda is the rate parameter. We say the mean and variance, the mean is given by 1 over lambda and the variance is given by 1 over lambda squared. We say the exponential distribution has a memoryless property. By memoryless property, what we mean is that the for any non-negative number s and t, the following holds. The probability of the random variable greater than s plus t, given x is greater than s, is equal to the probability that the random variable is greater than t. I believe we understand this. I'll explain many functions like this. Then also, it has non-negative values. It takes non-negative values as the exponential distribution. It has what we call the exponential decay, which means once it has reached a certain level, the rate is fast, is constant. It cannot go back. It is very, very fast. I can remember explaining that in our last class when I show in the other class in seminar for actuarial mathematics, when I showed the graph for the exponential distribution and how it started as decaying gradually, and then it reached a certain stage that the decay was fast. And we say that the decay is constant. It is constant. It's sure that it will continue going constantly. It can be slow, it can be very fast, but it cannot be backward. It can't go back. So that's why we say it has an exponential decay, which means that the events occur continuously and independently at a constant average rate over time. I remember explaining last time that when we have some claims, and especially maybe a rate whereby the claims start occurring very fast. Maybe we have some set of 60-year-old that have been buying an insurance, and then maybe you have 10 of them, and from that 60, that's when most times the probability of dying is faster than when someone is young. So maybe at that age and you have insured like 10 or 50 people, for instance, you expect that very soon now the claim will be coming, and it will be coming faster because most of them will now start dying, and those who are claiming the who have the claims will start coming, and that will be very, very fast. So that's just like an example of the exponential uh, function, or what we're talking about, the exponential decay. It will have a constant events occur constantly, continuously and independently at a constant average rate over time. So it is often used to model the time between events in a Poisson process. So like I was saying earlier on, there's a similarity between the Poisson process and the exponential distribution. Application, it is commonly used in reliability engineering, so and so and so, blah, 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 blah. And then it's also used in survival analysis to model time until death. The gamma distributions application. Now, we remember we showed that the geometric probability function P of x gave the probability of x failures before the first success in a series of independent success failure trials. Remember, when we're looking for the number of times it fails before a success, we see that the geometric PDF give the probability of x failures before the first success in a series of independent trials. We also explained that the negative binomial probability function, I remember saying that the geometric distribution is a special case of the negative binomial distribution. So the negative binomial distribution gave the probability of x failures before the rth success in a series of independent success failure trials. All right. So the geometric distribution, which is discrete, and the negative binomial, which is discrete, are special cases of the gamma distribution. They are related. These three distributions are related. The gamma distribution is related to the exponential distribution in a similar way. The exponential random variable t can be used to model the waiting time for the first occurrence of an event of interest, such as the waiting time for the next accident at an intersection. The gamma random variable x can be used to model the waiting time for the nth occurrence of the event if successful occurrences are independent. Sorry, let me make a clarification. Uh, just like the geometric distribution is related to the negative binomial distribution, that's how the gamma distribution is related to the exponential distribution. All right, so the properties of the gamma distribution includes, this is what we have here. It is parameterized by two parameters, and theta, and it gives us this ugly function here for x greater than 0, that's the PDF, where k greater than 0 is the shape parameter. So k here is the shape parameter. I remember recording our last class when I was talking about shape parameter and the scale parameter. The shape parameter determines the shape of the distribution or tells us where the probability might lie, while the scale parameter scales the distribution. So theta greater than 0 is the scale parameter. The mean of the gamma distribution is the shape parameter times the scale parameter, that's k times theta, and then the variance is k times theta squared here. The gamma distribution does not have a memoryless property. Remember, we say it is related to the exponential distribution, and the exponential distribution has a memoryless property, which means it does not take into cognizance the event that happened before. But actually, what it means is that it decays at a continuous, constant, independent rate. But the gamma distribution does not have the memoryless property. Then the support of the gamma distribution is x greater than 0. The exponential distribution is a special case of the gamma distribution, and it is the the gamma distribution becomes an exponential distribution when k equals 1. So it reduces to the exponential distribution with rate parameter 1 over theta. So it can be used in to model waiting times and so on and so forth, and even natural science. Now, note that for alpha equals to 1, just like what we're explaining, can you remember the exponential distribution? So let's come to the gamma distribution here that we have. Let's say at what do we at k at k equals 1. Let's come back here. Our k. Let's say k equals 1. We have 1 over theta is theta, because theta will be k will be 1. 1 over theta, and we have gamma of 1, and we have 1 minus 1, which is 0. So x goes, and then we have minus x over theta. So therefore now our new function when k equals 1 here becomes 1 over theta times e 1 over theta times e to the power of x over theta, which is the exponential distribution, but having an inverse rate parameter, inverse rate 1 over theta as the inverse rate parameter. So let's look at it here more clearly. We see that here at alpha equals 1, there we represent it with k. Or here alpha equals 1, we see we have gamma of 1, we have beta raised to the power of 1, we have x raised to the power of 0, and we have minus beta. So this gives us the exponential distribution. So the exponential distribution is a special case of the gamma distribution where the shape parameter k is equal to 1. Now, this exponential density function, this is the exponential density function. So the exponential distribution is a special case of the gamma distribution. So here is the plot of the gamma distribution. As we can see here, this first distribution at alpha equals 1, or there initially we use k. You see that it gives us the plot of the exponential distribution. Remember, giving us the constant exponential decay. That's at alpha equals 1. From our last class, we gave a plot of the exponential distribution. Then at alpha equals 2, you see it gives, we say it is skewed. You see it's skewed to the what? To the right. And then at alpha equals 4, it gives another distribution. That's how it keeps on moving. Now, the familiar negative exponential curve for alpha equals 1 is clearly visible. For the higher values of alpha, the curve increases to a maximum and then decreases. So if just like we have in alpha equals 4, it increases to a maximum and then it decreases. Now, so now let's look at some applications now. Applications of all these distributions that we talked about. So we start with the first application that we have here, which I call example 2. In example 2 here, it says consider modeling the claim amount for a certain type of insurance policy. Okay, before we start talking about these applications, does anyone has contribution or questions or observation? Are we together?
Yes, we are.
Okay. Is there any, so far so good, is there any contribution or question or a place that need clarification?
So far, so good. But I observe that gamma of 1 is equals to 1. So I'm just taking it to be so
Okay, yeah.
based on that parameter that you
Okay,
show.
yeah, that's nice observation. Nice observation. I like that. So it shows that you are actually following, which is great, which is nice. Yeah, so gamma of 1 is equal to 1. Correct.
I'm that my following. I'm trying to copy Ebun. Well, I know she follows better than I
Okay,
do.
yeah.
That's very
Yeah.
good. It's always have someone to join you in the group. I appreciate that, Koinde.
Exactly. Just like I was telling her personally, I say to her, she's all those sharp students that when the math teacher gives assignment and he forgets to ask the assignment. All this one I will say, sir, you forget. When the those students are trying to be quiet so that the teacher will forget the assignments, they are the ones that will raise up their hands and say, sir, you forget the assignment that you gave us.
So it's just for me to learn better. I think the assignment or whatever. So I'm waiting for you to do the application before I start. I'm always believing that the theoretical aspect is there, but when it comes to the application, that's where my problem is anyway. So it's
Okay.
easy for you to see the formula to get everything, but applying it into real life is where my major problem is. And when I tend to kind of submit assignments, is because I want to know if I'm correct or not.
No, no, it's correct. You are right. I like
Yeah,
that. It's excellent. It's excellent. It's
thank you.
impressive. Well done. Keep it up. Yeah. So let's look at the some of the applications. Here in the first example, we have consider modeling the claim amount for a certain type of insurance policy, where claims can vary between 1,000 and $5,000. I think it should be. I think it's a typographical error, but it should be 1,000 or $5,000. Let's assign a price to it, or naira, as the case may be. So even without saying that it is a continuous uniform distribution, you remember the uniform distribution, we gave two intervals, A and B, the minimum and the maximum, which is A and B. And the PDF of the uniform distribution is 1 all over B minus A. Remember? Yeah. So it comes into play here. Since we're looking at this example, we say we want to model a claim amount for a certain type of insurance policy. And then the claims vary between, so you see there's no specific value, and that makes it continuous. It varies between 1,000 and 5,000 naira or dollar here. So the continuous uniform distribution can be used to represent this scenario where any claim amount between the set interval is equally likely. Remember, we say it varies, so there's no claim interval or particular value that has higher probability than the rest. So all the probabilities are equally likely. Remember, one of the properties of the continuous uniform distribution we mentioned, we say that all the probabilities are equally likely for all the intervals. Yeah. So the claim amount, if the claim amount vary between this interval, either from 1,000 to 5,000 or from 5,000 to 1,000, that gives us a continuous uniform distribution. And just like we say, it is the simplest of the continuous probability distribution. So we can just model it this way and we'll get our probability. I believe this is clear. So this will give us 1 over 4,000, which is equal to 0.0004, right? Which will give us the probability for anybody for a person to lay a claim that will lie between that particular interval. Is this example clear?
It is.
All right, thank you, sir. All right, to the next one. Now we can also use the exponential distribution to measure claim inter-arrival times. Claim inter-arrival times. I believe when we start, when Elias will start taking us on the practical exam, remember he said he has some practical insurance data that he has collected from some insurance company. So when he starts using those data, we will understand more and more of this, like all the claims, the claim inter-arrival times, and so on and so forth. But let's look at this scenario.
Sorry, I've raised my hands up.
Okay.
We've gotten the answer, the FFS, which is the probability function, is
Yes.
equal to this. For a layman, how can
Yes.
you interpret that? Are
That's
you
here.
saying that it will, yeah,
Here, right?
yeah. So because
Right.
the answer is 0.00025. So are we saying that the
Yes.
probability is so small that they're going to claim between that amount or what in a
Okay.
layman's language?
All right. In a layman's language and applying to insurance or
Yeah,
actuarial science, right?
yeah.
Now you see the probability model helps you to be able to calculate premium prices. You know, in insurance,
Yeah.
you we have the policy owner and the policy is it policy
Policy
holder
order.
and the policy what do we call the other policy maker or something like that, or
Is it
the
the underwriter?
that's the insurance the insurance company.
Yeah.
We have the insurance company, we have the policy holder, we
Uh-huh.
have what we call premium amounts, we
Yeah.
have what we call the claim amount.
Yeah.
The premium amount is the amount you pay to service the insurance,
Yeah.
whereas the claim amount is the amount you get for being insured as
For a
the amount
particular incident. Yes.
put. Now you see here we're talking about a particular claim amount that is
Yeah.
being paid. Yeah. So now that the if you get the probability,
Yeah.
you multiply by the uh, premium, which will give you the exact premium that you need to be charging, whether per month or per year.
Okay.
You
That's kind
understand?
of a pricing it. Oh, okay. Okay. Okay.
Ehen. So the probability helps you to price.
Okay.
And sometimes the higher the probability, the lower the price, and then the higher the probability, the lower the price, and then the lower the probability, the higher the price. I don't know whether you understand.
Ah, okay. So
Mm,
like this one
yes.
is very low now.
Yeah. So it's very
So
low.
mm,
So you get back.
yeah, yeah. Okay. So
So this
the
is why we
higher the
calculate.
probability, the lower the premium, and the lower the, so it's vice versa.
Yeah, the vice versa. Because the more you are going to get, the more the insurance company believe that it's easier for you to make claim.
Yeah.
Do you understand? If they know
Yeah.
that it's easier for you make claim anytime soon,
Yeah.
then the claim amount becomes very small. But
Is
if
it
it seems as though
is it
you're not going to
the
make,
claim amount will be small?
yeah,
Okay, but the
yes,
premium will be higher.
yeah, the premium will be higher. But
Uh-huh.
if they feel like at any moment you can lay claim, or it will
Mm,
take a longer time or shorter time, you see, with this idea of the probability, it helps you to be able to know how much okay you can charge as premium, and then how
okay.
much you can set as your claim amount for any
Okay.
pre-insurance policy that you want to make.
Okay.
Yeah.
All right. Thank you. That's just the way I just love to explain in a layman's language. Yeah.
Yeah, we can also go online and make more research to get more and more of the information. But I believe that when Elias will start use teaching us how to calculate premium using the claim severity and frequency approach, or
Okay.
severity and frequency approach, we will get more and more understanding of
Understanding.
these
Thank you very
probabilities.
much. Yeah.
Yeah. Because there's a formula that you use, you multiply this probability density function by the frequency or the probability, then you now
Mm.
add something. There are some things
Yeah,
that
he
you,
mentioned something that like cushion it.
yes,
Yeah, he mentioned
exactly,
a lot of things. Yeah, that it's not just this one, but you had other things to it before
yes,
yeah,
before you get the premium and
yeah,
then the other values. Yeah,
charges.
correct.
Then yeah, that's good. Thank you.
Then we call that the utility function.
Okay.
Yeah, if when you make more research, you get
All
what
right.
I'm talking
Thank
about
you.
here.
Yeah.
Okay, we're looking at this scenario. We say suppose an insurance company wants to model the time between consecutive claims for a specific type of insurance. Immediately you hear consecutive claims, it means that it is continuously and constant, which takes us back to the exponential distribution. Remember? Yeah, because the exponential distribution, we say it models continuous and independently constant events. So, suppose an insurance company want to model the time between consecutive claims for a specific type of insurance policy. One, the exponential distribution can be used to model the inter-arrival times between claims. Let's say the average time between claims for this policy is 30 days. So we have 1 over 30 as our average value, average rate, and then To solve this, we use the the exponential distribution to find the probability, and then we substitute lambda to be 1 over 30 here. So here we have 1 over 30 times e to the power of 1 over 30, uh, uh, then x. Then x here will be our number of claims occurring within a certain interval per period. So we'll do that to get the expected number of claims in a given time frame. Take for instance, if the question asks um, the number of claims in 2 days, in 1 day, in 5 days, so that will be our x, and so on and so forth. In more than 30 days, then we are sure that it is equal to 1. Remember, because it's equal to 0, it's equal to 1. That's if it is greater than that value. But if it is less than that particular value, then it is 0. Like in 0 days, that's 0. Because we are sure that in no day there's no claim that will come, so it is 0. But if it is more than 30 days, we are sure that a claim will come. Yes, if it is more than 30 days, we are sure that a claim, there's no, it will be more than 30 days and there's no claim, so it is equal to 1. That's a sure. That's very certain. Now, another example, let's look at this scenario. An insurance company wants to analyze the time until policyholders renew their insurance policy. So we can use the exponential distribution here to model the time until policyholders renew their policy. So in doing that, we assume that the average time until policy renewal is 1 year. So the rate will be 1 over 1, which is 1. So we use the exponential distribution to estimate the probability that the policyholder will renew their policy within a certain time frame. That certain time frame is our X. So this information can help the insurance company manage policy expiration and renewal strategies effectively. So this is some of the importance of the calculating the probability. It helps the company to manage policy expiration. They will know where and when the policy will expire, and then which strategies they can adopt to renew this policy effectively. So when we have specific values, we can input them and get specific values. But I believe that this example uh, gives us more like an idea. Yes. So when we start dealing with real values, other practical problems, we can get it more. And I encourage us to also go online. When you go online, you look for questions and then you bring it here so that we will discuss, so that the class will not be more of theory, but it will be more of discussion and understanding. So I would like to encourage us, if you go online or you consult textbooks or books or questions, you can see questions that relates to these distributions that we're talking about, and then you bring them here, we discuss them, we look at possible solutions and how to understand them better and to make some other deliberations and conclusions. Then also, another example will be if you want to measure the time until equipment failure. This is a survival analysis. An insurance company insures manufacturing equipment and wants to predict the time until equipment failure. The exponential distribution can model the time until equipment failure occurs. So how do we solve it now? We look at, say for instance, we're looking at an average time until maybe the equipment fails in 5 years. So our rate parameter will now be 1 over 5. That will be our rate parameter. And then we can also measure a specific time. We say, okay, in 1 year, in 2 years, in greater than 5 years or less than 5 years, which should be our X. So this information will help the insurance company to determine appropriate coverage and pricing for insuring equipment against failure. Now, another application is in calculating claim amounts. So we can here we can find the normal distribution very useful in that. So let's look at this scenario. An insurance company wants to model the distribution of claim amounts for a particular type of insurance policy. So they want to measure the distribution or behavior of claim amounts for a particular type of insurance policy. It may be life insurance, health insurance, motor insurance, or even emerging insurance uh, like cyber insurance and so on and so forth. So the this is the application now. The normal distribution can be used to model claim amounts, especially when the claim amounts are continuous and symmetrically distributed around a mean value. Take for instance, let's assume that the mean claim amount is $10,000 and the standard deviation is $2,000. So we have our mu to be 10,000 and our standard deviation to be 2,000. So we can use the normal distribution to estimate the probability that a randomly selected claim amount, falls within a certain range. So as usual, this information will help the insurance company to manage its financial reserves and pricing strategy, because without this information, and the insurance company did not manage its financial reserves and use it maybe without being managed, if a particular claim comes and there's no money in the reserve, then they will go bankrupt. But with this information, it actually help them to manage their financial reserves, and then it will also help them to know how to price effectively. Then another practical application of the normal distribution is in this scenario, and so on and so forth. Now, it's also similar to the ones we have done earlier on. Once when you go through, you can see them and understand better. So we can also use the normal distribution in loss ratio using this example, and so on and so forth. Now, in summary, we have looked at the continuous probability distribution, and we say it models events in a range that are continuous, unlike the discrete distribution that measure specific claim amounts. The specific claim amounts, the continuous distribution measures claim amounts within an interval or a range. And we say practically we are only in the discrete, we are looking at integers, while for the continuous we are looking at values that are decimals or continuous. So we explain some properties of the normal distribution. We say it is symmetric and have a bell-shaped curve. We say the mean determines the central location while the standard deviation controls the spread. We see that one of the empirical rule, can you remember one time that we were talking about the empirical rule? We say approximately 68% or 95% and 99.7% of the data fall between 1, 2, and 3 standard deviations from the mean respectively. And we say it is widely used in insurance, finance, and natural sciences. The exponential distribution, we say it models time between events in a Poisson process. And we say it has memoryless property because they occur the occurrence in the next interval is independent of past intervals. And we say it has a continuous independent occurrence. We say it has rate parameter lambda, which determines the average rate of occurrence. It is commonly used in reliability engineering and queuing theory. We say for the uniform distribution, it has constant probability density over a specified interval. It usually have a specified interval A and B, just like we give that example of claim amounts, $5,000 and $1,000. We see all outcomes are equally likely within that interval. And then the parameters, we have the lower band, which is represented by A, and the upper band, which is represented by B. And I would say it's also applied in random number generation and modeling continuous phenomena. Then the chi-square distribution, we see sum of squares of independent standard normal variables. It has K as degree of freedom. It is used in hypothesis testing, confidence interval estimation, and goodness of fit test. We see the student T distribution is similar to the standard normal distribution, but it has heavier tails. It has K degrees of freedom. It is widely used in hypothesis testing and confidence interval estimation, especially with small sample sizes. And then this other one that we have not talked about, which is the log normal distribution. I remember in one of the class we say it is taking the log of the normal distribution, you get the log normal distribution of the random variables of the normal distribution process, you get the log normal distribution. So this results from exponentiating a normal random variable. It is useful for modeling risk data such as asset prices and income. And then it has location parameter mu and shape parameter sigma. And in conclusion, next class we will talk about some other univariate continuous distributions, which will include the Cauchy distribution, the logistic distribution, the Pareto distribution, and the beta distribution. Then exercises. These are exercises for the next class. Are we all there?
Yes, we are here.
Yeah. We are here.
All right, sir.
We're here.
So, all right, correct. That's nice. So for our next class, our exercise will be we are going to read and write on the following distributions. So you will present your findings and the applications, and it will be discussed in the next class. So I think since we are everybody should do it, but specifically let's give Mrs. Abun the culture and logistics distribution. Let's give Mr. Osawo the Pareto distribution. Okay, no, let's do all. Let everyone do all. Is that okay?
Okay.
Yeah, let's do all. Then when we come on that day, we will now present accordingly, depending on those who are in class. The presentation will take marks too. Aside the assignment, the presentation will take some marks. So we'll just write, we'll read and write on these three distributions: the Cauchy, the Cauchy, the logistic, the Pareto, and the beta distributions. All right. Thank you all for listening, and thank you all for being in the class up to now. So if there's any questions, contributions, comments, observations, please go ahead. Is anyone raising his hands? I want to believe there's no. Okay, go ahead. Go
Yeah.
ahead.
Sorry. Are we getting the
Battery.
hello?
Yes, I'm with you, sir.
Okay. Are we getting this course content? I mean this particular slide.
Yes. They are all in the drive.
The
They are
drive.
all in the
Okay.
drive, except you have not been looking at it. All from the
No,
first
what
lecture.
is asking, if I'm right, is will you release this particular one on
Yes,
time
yes.
so
Yeah,
that we
I'll
can
release
do
it.
the
I'll,
assignment?
I'll,
That's what I think is trying to ask.
I'll release it. I'll even release it this night, sir.
Thank you.
Okay.
Yeah, I'll release it this night.
Okay. Which drive are you also talking about?
There's a specific drive that we usually post in the actuarial mathematics group. We say follow this drive to find,
On WhatsApp?
to locate lecture notes, classes,
Is it on WhatsApp?
it's on WhatsApp. Yes. Once you just log into that
Okay.
drive, you will go there. You will
Okay.
now see
All right.
actuarial mathematics. You will select
Okay.
probability theory and
All right.
distribution. You will see under
Okay.
that you will see material. You even see the textbooks I'm using for these classes there. The textbooks, the materials
Okay.
in PDF, the videos, the assignment questions, and so on and so forth.
Okay. Then number two, this our Telegram group.
Yes,
What's
sir.
going on there? Because I don't probably I'm missing some things on the group. We are not it's not active.
It's not active, right? Okay, I will.
Yes,
Okay.
yes.
All right. We are supposed to be posting the videos there for easy accessibility,
Oh,
but
okay.
I'll talk to them so that it will be much more active.
Okay, I thought I'm missing something because I'm not. I go there to check, but nothing.
Okay. Okay. No. It's supposed to be more of the videos there. So we'll do something about that.
All right. Thank you.
Yes, you're welcome, Sam. All right. So, if there's no any other question or comments, I would like to say thank you all for being in the class and enjoy your night. We meet again next week.
Oh,
Thank you
thank
very
you.
much.
Good
All right.
night, everyone. Bye.
Have a great
Bye.
night.
Yeah, good night.